Hi. In the previous lecture, we covered the time dilation equations for Einstein's special relativity. In this lecture, I want to cover length contraction. So we define length contraction according to the measured distance between 2 points is going to depend upon the frame of reference of the observer. So we're going to define the proper length of an object as the length of the object as measured by someone at rest relative to that object. And the length of an object measured in a reference frame that's moving with respect to the object is always going to be less than that proper length, hence the term length contraction. So just as in time dilation, it's really important to correctly identify the observer who measures that proper length, okay? The equations themselves are not difficult to manipulate. It's really pretty easy to do, but sometimes figuring out which length is the proper length, that is kind of tricky, okay? So just remember that the proper length is going to be the length measured by the observer at rest with respect to the object, with respect to the endpoints of the object. Now sometimes the proper time interval and the proper length are not measured by the same observer. This is a little bit confusing, but hopefully it'll help when I work an example later in the lecture. Okay, so what's the length contraction equation? Length contraction takes place only along the direction of motion. This is an important point to remember, okay? So, for example, if you have a meter stick that's traveling along, okay, parallel to its long axis, its velocity is parallel to its long axis, then the length of that object would look like less than 1 meter from outside the reference frame. Now, however, if you turn that meter stick so that the long axis is perpendicular to the direction of travel, okay, then the meter stick is still going to look 1 meter long. It'll look skinnier though, okay? It'll look like a much skinnier meter stick, but it'll still be a meter. The equation for length contraction is given here in this slide. L, which is the contraction length, is equal to L naught over gamma, where L naught is the proper length, okay, and gamma is 1 over the square root of 1 minus u squared over c squared. Now because it's 1 over that square root and gamma is in the bottom of the fraction, when you solve through for this, you get L is equal to L naught times the square root of 1 minus u squared times c squared, or 1 minus u squared over c squared. Okay, now I have an active figure that I'd like to show you on this little idea, and this active figure is courtesy of Thompson Higher Education. All right, here's the active figure. We have 2 meter sticks here. One is by observer A, as observed by observer A, which is at rest with respect to the meter stick. Maybe they're on the same spaceship or something, okay? And you can see that the fixed stars are moving there behind the meter stick, and it's 1 meter long, all right? Now here you have observer B. Observer B is still with respect to those fixed stars, and you can see the meter stick cruising by. Now, since we're only at 30% of the speed of light or so, the difference is not very large for the proper length and the observed length for observer B. It's only 1 versus 0.95, okay? So there's not much of a difference. But let's jack it up so that you can really see what's going on here. It's accelerating now, and it's going to reach 98% of the speed of light in just a second or two. All right, so now it's really booking. Okay, the meter stick is going at 98% the speed of light, and the observer B, which is at rest with respect to the fixed stars, shows a length of only 0.2 meters. So it's really a lot shorter and stubbier of a meter stick than it was at 30% the speed of light, and you can really see the effects of the length contraction now. Now you might think, well, this is just an illusion. It just looks shorter because it's going by so fast. But the reality is it actually is that short for observer B, and we'll talk more about this with an example later in this lecture. So it really is that short. It's important to remember this. Okay, now the proper length and the proper time interval are defined differently. This becomes important a little bit more when we get into some of the problems with the Lorentz contraction equations that we'll cover in another lecture. But just to make sure that we cover it here, the proper length is measured by an observer for whom the endpoints of the length, the endpoints of the object, remain fixed in space. Okay? The proper time interval is measured by someone for whom the 2 events take place at the same position in space. Okay? So this may seem like nitpicking, but we'll talk more about this later. Okay, let me do an example for you of a length contraction problem. So here we have an astronaut on a spaceship. When the astronaut's here on Earth, his height is 6 feet. and he decides to take a nap, I guess, maybe, to rest up, because I've heard space flights can be kind of long. And he's lying parallel to the axis of the spacecraft, moving at 0.9 c relative to Earth. So in other words, the spacecraft's moving along like this, his bed is parallel to the axis of the spacecraft, so he's parallel to the direction of motion when he lies down. So what's his height as measured by an observer in the spacecraft with him, and also by an observer looking at him from the surface of the Earth? Well, the simple question is, how tall is he to somebody on the spacecraft? Because on the spacecraft with him, nothing looks different. He's still 6 feet tall if you're with him on the spacecraft. This becomes your proper length L0. Now, to an observer on Earth, his length would look contracted. It would be contracted by a factor of gamma, which, as you remember, is 1 over the square root of 1 minus u squared over c squared. So if you plug in for what the speed of the reference frame is, 0.9 c, with respect to the stationary frame, then you get gamma is equal to 2.294. And then you would see that the contracted length L would be equal to the proper length, 6 feet, divided by gamma, 2.294, and you would arrive at a measured height of the astronaut of 2.62 feet. So to an observer on Earth, the astronaut would appear sort of shorter, but he would be the same width as he would be here on Earth, so he would be shorter and much more compact. Okay? All right. Next concept I'd like to cover is the twin paradox. And this kind of lies at the root of which is the proper length and which is the proper time and what the heck is going on with all of this anyway. Okay? So here's the twin paradox, the setup. You have two twins, Mary and Frank, and they're 30, and they decide on 2 different career paths. Mary is the moving twin, Mary, M for moving. She decides to become an astronaut and leave on a trip that's 8 light years from Earth. So she's going to a distant star that's 8 light years away, and then she's turning around and coming back to Earth. Okay? The speed is pretty great. It's a decent fraction of the speed of light, so gamma is going to be a relatively large number. Frank is the fixed twin. He decides to reside on Earth. So here's the paradox. On Mary's return, Frank thinks during her trip that her clocks measuring her age run slow. So if he were to observe things on her spaceship, everything looks kind of slowed down and sluggish. Okay? So as such, she's going to come back and she's going to be younger than he is because her clock is ticking slower than his clock. That means time passes faster for him and he ages faster. Now Mary claims that it's Frank who's moving away from her. So she's fixed on her spacecraft and she sees Earth moving away from her. So she thinks Frank's moving. And when she observes things, once she gets up to speed, when she observes things on Earth, they look like they're sluggish, okay? So it looks like Frank's kind of slowly moving through life, okay? So she thinks, well, Frank will be younger when I get back, okay? Who's right? That's the paradox, okay? Special relativity teaches us that all inertial frames should be equally valid. So here's a setup where it looks like there might not be 2 equally valid claims because somebody, when they get back, has to be younger. Who is it? Here's the resolution. Frank's clock's in an inertial system during the trip. He's on Earth, he stays on Earth, he never really changes speed very much, okay, at least not to a decent fraction of the speed of light, so gamma is very close to 1 for him the entire time. Mary, though, she's different. She gets on the spaceship. The spaceship starts from basically a speed of 0 to a speed that's a very good fraction of the speed of light, so she accelerates to very close to the speed of light. Then when she gets to the star, she has to turn around and come back. Remember that a change of direction is an acceleration because you're changing the direction of your velocity. So she's accelerating again then. Yet again, not an inertial frame of reference. Then when she gets back to Earth, she's got to slow down and land, which means she comes to a stop. So she decelerates there. So on several occasions throughout the trip, Mary's got to change her direction or her speed, which means she's accelerating, which means Frank is in the inertial frame and not her. Okay? So what this means, basically, is that Mary's wrong and Frank is right in this case. And so that's who decides who's younger, Frank. Well, let me go through an example of how to work a twin paradox problem because they can be a little confusing and hopefully work through this and clarify a few things. So here's the problem. The number is going to be a little different than the example that I gave earlier, so don't let that confuse you. A woman leaves Earth in a spacecraft that makes a round trip to the nearest star. The star is 4 light years away. The speed, once they reach it, is 0.9 c, or 90% the speed of light. How much younger is the twin that traveled in the spacecraft on her return than her twin sister who remained behind on Earth and didn't go? Well, the way that we're going to solve this is we're going to solve for a time that it takes the twin traveling to the distant star and back, and then we're going to use the time dilation equations to solve for the other measured time. Okay? Then we're going to get the difference between those two times. So first we have to get a time. Okay? Now, we don't have a time in this equation. We have 4 light years distance. Okay, so we have a distance, and we have a speed, 0.9 c. So we have a speed and we have a distance. So we can use speed is equal to distance divided by time and solve for the time that we need to churn through this problem. Okay? Now, a lot of students would then take that 0.9 c, convert everything to meters per second, and go through and churn through it. I'm going to show you a slightly easier way. We're going to use a fun unit conversion to make the problem a little simpler. The speed of light is, of course, 3 times 10 to the 8th meters per second, but you don't necessarily have to use meters per second all the time, not if it's not convenient. You could use more convenient units for the speed of light, if it helps, and it's gonna in this case. One convenient unit for a speed is that c is equal to 1 light year per year, okay? And that's because a light year is defined as the distance that light travels in 1 year, okay? So c is 3 times 10 to the 8th meters per second, or c is 1 light year per year. So we're going to make that unit choice, okay? So here we have 0.9 c is 0.91 times 1 light year per year, okay? And then we're going to set that equal to the distance divided by the time. Remember, it's a round trip. She's got to go to the star, which is 4 light years away, and come back. That makes the total distance traveled 8 light years. So here we have 0.9 times 1 light year per year is equal to 8 light years divided by delta t. And then we solve for that delta t, and we get 8.9 years, okay? So according to the twin on Earth, it takes 8.9 years for that trip to take place, okay? All right, so moving on to figure out the rest of the problem. The woman in the spacecraft undergoes acceleration, and the twin sister on Earth is in the inertial frame. Now here, it's the proper time gets kind of confusing. The proper time is associated with the inertial frame of the sister on the spaceship because it's really her age that's in question here, okay? So since it's her age that's in question, her heartbeat's measuring it, her reference frame is going to be the proper time in this case. Okay, so now we have to solve for gamma. Gamma is equal to 1 over the square root of 1 minus u squared over c squared. In this case, that gives us 2.294 when the speed is 90% the speed of light. Okay, so using our equation for time dilation, delta t is equal to gamma delta t naught. So the 8.9 years, that's as measured by the twin on Earth. That's the dilated time. Okay, that's the longer time. So here we have 8.9 years is equal to 2.294 times delta t naught. Delta t naught is the proper time, or the age of the sister that's on the spacecraft. Okay? So now we solve for delta t naught, and delta t naught is equal to 8.9 divided by 2.294, and we get delta t naught is equal to 3.9 years. So according to the person on the spacecraft, 3.9 years have passed. According to the person on Earth, 8.9 years have passed. That's why the person on Earth is older. How much older? Well, we're going to subtract those two numbers. 8.9 years minus 3.9 years, that gives us 5 years. So the twin on the spacecraft is younger by 5 years than the twin that remained on Earth. Okay? Now, let's talk a little bit about sanity checks. Sanity question mark checks, I guess, at this point, because special relativity has been known to drive even the best person a little crazy, all right? Here's what they should agree on, though. They should agree on their relative speeds. So the twin on Earth agrees that the twin on the spaceship is traveling away from her at 0.9 c. The twin on the spaceship says, yes, it's 0.9 c, but you're going that way away from me. But they both agree it's 0.9 c. Now here's the thing. That 8 light years distance, that's measured by the stationary twin. The moving twin, she would see a contracted length. So she wouldn't say, I traveled 8 light years round trip. She would say a different length. Okay? She would say a shorter length. So the length that she would see would be L naught over gamma, the proper length, because that's the stationary fixed points, right? So the person on Earth, They start, they come back, it's a fixed point, okay? Nothing's changed there. So you have 8 light years divided by 2.294, and that gives you 3.5 light years as measured by the twin on the spaceship. So the twin on the spaceship thinks she only traveled 3.5 light years, all right? Now, the moving twin, okay, she's going to see a 3.5 light year distance traveled divided by a 3.9 year span of time, right? So 3.5 divided by 3.9 gives you 0.9 light years per year. They agree on their speed. The stationary twin sees an 8 light year distance, okay, and she sees 8.9 years pass. 8 divided by 8.9 gives you 0.9 light years per year. So they both agree on the speed, okay? Now, however, the moving twin, that person sees a contracted length. So the moving twin does not see the proper length, but the moving twin does see the proper time. The stationary twin sees the proper length, but the stationary twin does not see the proper time. So sometimes the proper time and the proper length are in different frames of reference. All right? So hopefully this twin paradox example cements some things for you about length contraction and time dilation. Okay? Feel free to play this video as many times as you like, and you might have to think about it for yourself a little bit because it's a brain bender. Okay? Nobody ever said relativity was easy. All right. I'll see you in class.